Let's do some problems where we identify the relative extrema of various functions. We're going to start with problem 2. So here we have a function f of x, which is equal to x squared plus 8x plus 10. Now this is a quadratic. It's kind of nice. If we were doing what we were doing before and identifying the domain, remember quadratic or any polynomial has domain all real numbers. So in a way, the domain here is not too relevant because it just doesn't exclude anything. We want to do exactly the same thing that we were doing when we were trying to find where a function is increasing or decreasing. So that means we are going to start with the derivative. Derivative here, hopefully by this point you know how to differentiate a quadratic pretty well. X squared becomes 2x, 8x becomes 8, and the 10 goes away. We're looking for critical points, so we're going to set this equal to 0. Solve for x. And we get a single critical point here of x equals -4. Now, of course, the other part of critical points is where the derivative doesn't exist, but we don't have any problem with 2x plus 8. That always exists. So we have one single critical point. We can even go ahead and just make our number line right away. Put in -4. Now we want to identify whether or not the derivative is positive or negative on these intervals. So from -infinity to -4, do we have a positive or negative value? I just have to pick a test point, so some number that's less than -4, and plug it into my derivative. I'll just go ahead and pick -5. So what is the derivative at -5? Well, there we have 2 times -5, or -10, plus 8, which gives us a -2. So our derivative is always negative from -infinity to -4. On the other side, go ahead and stick in, actually, might as well go ahead and pick 0. If I plug 0 into here, the 2x goes away. We're left with an 8. 8 is a positive number, so the derivative is always positive from -4 on to infinity. What does this mean? This means that our function is decreasing and until we get to -4, and then it's increasing afterwards. In fact, we can kind of get an idea of what it looks like. It has to be decreasing. It hits a horizontal tangent line here at -4, and then it has to increase from that point on. What we have is a relative minimum. Now, if we do want to identify what that minimum actually is, what we're going to have to do is take this -4 and plug it back into the original function, not the derivative here. The derivative is just going to give us 0 because that's how we found the -4. We want to know what the value of the function is. So f of -4, so we have -4 squared is a positive 16. Then we have 8 times -4, -32. And then we saw the plus 10, which gives us a -6. So it bottoms out at the point -4, -6. And -6 is the relative minimum. Really, it's going to be the absolute minimum of this function over this entire graph, in fact. Of course, if we go ahead and graph this, so our function was x squared plus 8x plus 10. We can see here that we have the minimum of -4, -6 is the bottom point, or the vertex of this parabola. Is decreasing here, is increasing here. All of this consistent with what we just found. Next, let's do problem 6. We have a function g of x is equal to 1/3 x cubed minus x. Like before, we'll go ahead and identify its domain. Because this is a polynomial, it's going to be domain all real numbers. We still proceed the same way. We start with the derivative. So the derivative of this, well, the x cubed becomes a 3x squared, but the 1/3 there gets rid of the 3. So we're just left with an x squared for that part. And then the minus x becomes a negative 1. Of course, we're setting this equal to 0. To find those critical points, we can factor x squared minus 1 as x minus 1 times x plus 1. And so we get, from here, we get x is 1. From here, we get x is negative 1. Or in other words, we have x is plus or minus 1. X squared minus 1 always exists. We don't have to worry about that part of critical points. And so our number line just looks like this. We have a negative 1 here and a 1 here. And we want to identify whether or not the derivative is positive or negative on each of these 3 intervals. Well, we can start with the middle one, because that one includes 0. Why did I put f? It's supposed to be g prime of 0. What happens if we plug 0 into x squared minus 1? Well, the x squared goes away. We solve the minus 1. So our derivative is negative from negative 1 to 1. From 1 on, go ahead and pick 2, smallest integer that we can. There, x squared is 4. We still have the minus 1, so we get a positive 3. And finally, on the other side, we go, it's kind of nice and symmetric, so we might as well pick negative 2. And in fact, the square is going to get rid of the negative anyways, so we're going to get the same result as we got for 2. We get a positive 3. So we get, it's increasing here, it's decreasing here, and it's increasing here. So at negative 1, it switches from increasing to decreasing. So as you can kind of tell already, we're going to have a relative maximum. It's definitely going to be essentially the top of a hill. At 1, it's going to go from decreasing to increasing. So it's going to be the bottom of a valley. It's a relative minimum. Let's go ahead and actually plot this function. So you have 1/3 x cubed minus x. We have this function here. Note that at negative 1 and 1, we have a relative maximum and a relative minimum. Go ahead and just put those in there. We have a relative maximum at A, a relative minimum at B, where the x values are negative 1 and 1. Now note, in this case, these are not absolute maximums or minimums. In fact, we definitely have points over here. Any point after x equals 2, we have a higher point than we have at negative 1. Any point below, any x value below negative 2, gives us a value that's lower than our relative minimum. But in a region, say from negative 1.5 to negative 1.5 to negative 0.5, A is our highest point. If we only look at that little section, we do have a highest point here. It is the maximum on that interval, and that's what we're trying to find. Let's move on to problem 12. We have another function, f of x. This time it's equal to 3x minus 36 x to the 1/3 power. If we look at the domain of this function, obviously the 3x doesn't have any problems, and actually the cube root here, that's what x to the 1/3 power is, the cube root doesn't have any problem for any value of x either. So actually this function has domain all real numbers. We haven't really had to worry about the domain yet, but we will in the next problem. Again, we start off by taking the derivative. Derivative of 3x is just 3. Derivative of x to the 1/3 power is going to be 1/3 times x to the negative 2/3 power. Well, the 1/3 that we bring out, we bring down that 1/3, it's going to combine with the 36 that we have there. 36 divided by 3 is a 12. And then our new power, because we subtract 1 from the 1/3, is going to be a negative 2/3. If we set this equal to 0, essentially we move the 12 times x to the negative 2/3 over to one side. I am now going to actually divide everything by 3 and multiply by x to the 2/3. That's going to make it x to the 2/3 over here, and it's going to give us a 4 here, because we divide that 12 by that 3. But at least we don't have any negative exponents now. Next, I want to get rid of the over 3 part. That means I'm going to cube both sides of this. That's just going to turn this into an x squared over here. 4 cubed, that is actually 64. And then if I take the square root, square root of 64 is 8 or negative 8. Don't forget that negative there. We actually do have 2 critical points from that. We have one at negative 8, we have one at 8. But we're not quite done, because this derivative actually doesn't exist at a point. At x equals 0, because x to the minus 2/3 is actually a fraction, remember this is 1 over x to the 2/3 power, this expression doesn't exist at x equals 0. So let's just, f prime of 0 does not exist. That means that 0 is going to be a critical point as well. But note here, it's only a critical point because 0 is in the domain. We are allowed to put 0 into the function, just not the derivative. This is a critical point and not a discontinuity. So we'll put 0 here, we'll have negative 8 and 8. And we want to identify what's happening on each of these intervals. So I'm going to go ahead and just pick some numbers, plug them in. Say from negative 8 to 0, we can go ahead and pick negative 1. That's a nice enough number. There we have 3 minus 12 times negative 1 to the negative 2/3 power. Because of the 2 here, that essentially we take the negative and get rid of the negative. So really we're just taking 3 minus 12. Negative 1 to the negative 2/3 power is a positive 1. When we subtract those, we get a negative 9. So our function is decreasing on negative 8 to 0. We have a negative derivative there the whole way. Same thing from 0 to 8. The derivative at 1. In fact, exactly the same thing. This x to the minus 2/3 actually turns into a positive 1 again. So we have 3 minus 12, or negative 9, is actually decreasing there as well. Now for negative infinity to negative 8, if I were to pick the negative 9, the closest integer to negative 8, that would actually be a little bit tricky to work with. I mean, you could use a calculator to work with it. But I'm going to go ahead and pick a number where I can take this cube root really easily. Unfortunately, negative 8 is already a cube, so I have to go to the next cube, which is negative 27. But when I do that, well, I still have the 3. And now I have 12. And then we have to take the negative 27 to the negative 2/3 power. That means I'm taking the cube root of 27, which is 3. Then I'm squaring it and getting 9. But then, because of the negative, it is on the bottom. So really I'm taking this 12 and I'm dividing it by 9. So this is 3 minus 4/3, if we simplify that. And we combine those two fractions, get a 5/3. So a long-winded way of saying our derivative is positive from negative infinity to negative 8. Now we don't have to do too much work to look at the 8 to infinity. If we plug in 27 like we plugged in negative 27 here, well, the square here was already getting rid of any negatives that we had from our input. So we're actually going to get exactly the same 5/3 over here. So we have our number line. And we can see from this that our function was increasing and switched to decreasing at negative 8. So it has a relative maximum at negative 8. At 8, it went from decreasing, it was going down, and switched to increasing. So we bottomed out, we have a relative minimum. But at 0, even though 0 is a critical point, is a full-on critical point, it's not a discontinuity, the function does not stop at 0. It's decreasing. It kind of does something at 0, and then it continues decreasing. It's not a relative maximum or relative minimum. We can even see how that works by looking at our graph. So if we have our function, f of x is 3x minus 36x to the 1/3 power. Can't really see too much of it. It looks like it's a vertical line, which really it can't be. Really the point here is that the y values got really big. So we need to scale down our y's. But we have our critical points. We had 0, 0, that has a point on it. We have 8, then f of 8. Then we have negative 8 and f of negative 8. There. We have 3 points. We have a relative maximum up here. It's not. This is the highest point on this section. It might be a little, it's not as sharp of a high point as was in some of our previous examples. But the point here is that it does reach a maximum and start moving downward at that point. Same kind of thing here. It was moving downward, now it starts moving upward at that point. That is the lowest point. At 0, we didn't have a relative maximum or minimum. It was a critical point specifically because we have a vertical tangent line there. But that does not mean that we actually had a high or low point at x equals 0. Now let's look at problem 16. Here we have a function f of x is equal to 9x plus 4 over x. This is an example of a function where the domain does not include all real numbers. Our domain is everything except for 0. We can't plug 0 into this function. Let's go ahead and write that as x, where x is not 0. We'll go ahead and start the same way we were doing before. We're going to take the derivative. Derivative of 9x is, of course, 9. For 4 over x, we're going to have to remember that x on the bottom here is really an x to the minus 1 power. That means that minus 1 power we're going to have to pull out. And then we're going to have to reduce the minus 1 power to a minus 2 power. Which means that we end up with an x squared on the bottom. Now we're going to take this derivative. We're going to set it equal to 0. In other words, if we bring the 4 over x squared over to the other side, we have 9 equals 4 over x squared. I'm going to go ahead and multiply each side by x squared, but I'm also going to divide by 9. In other words, I'm going to kind of switch the positions of the 9 and the x squared. We have x squared is equal to 4 over 9. And now I can take the square root. The square root of 4 over 9, well, actually, we can just take the square root of top and bottom separately. Square root of 4 is 2. Square root of 9 is 3. But then we have to remember that we can have a plus or a minus. Now we can also note here that the derivative doesn't exist at 0 because of this x squared on the bottom. But this time, because 0 is not in our domain, it's a discontinuity. It's not a critical point at 0. That doesn't change what we're going to do with 0, though. We're still going to put it on our number line. So our number line this time includes both of our critical points and the discontinuity. And we're going to go ahead and pick various test points in our intervals. This time we're not going to be able to completely avoid using fractions. We can do it for the outer ones. We could pick, say, over here, negative 1, and over here we can pick a positive 1. So what's f prime of negative 1? It's going to be 9 minus 4 over 1. So 9 minus 4, or 5. Same thing with positive 1. 9 minus 4, or 5. So we have a positive derivative before negative 2/3 and after 2/3. From negative 2/3 to 0, the fraction with the lowest denominator there would be a negative 1/2. Then we have 9 minus 4 over the square of negative 1/2. Well, the square of negative 1/2 is 1/4. When we're dividing by 1/4, that means we end up multiplying by 4. So really we're going to take 4 times 4. So we actually have 9 minus 16. That's a negative 7. And exactly the same thing for positive 1/2. Because the square got rid of our negative. So in both cases, we have a negative derivative on those two intervals. This number line actually looks very similar to what we had over here. So we had positive, negative, negative, positive. We still have positive, negative, negative, positive. Different x values, but the same format to it. So we're still going to have some of the same results. We have a relative maximum at negative 2/3 and a relative minimum at 2/3. Of course, at 0, even if we had a value for the function, even if the function did exist there, it wouldn't be either one. But keep in mind, technically looking at 0 here, we can't really use the first derivative test because this is not actually a critical point. F of 0 just simply doesn't exist there. So there's not really anything to identify. If we look at the graph of this one this time, so we have 9x plus 4 over x, we get this graph here. And actually, it's kind of good that I didn't rescale my y-axis back, because this actually is relatively big on the y values again as well. But you can kind of see here that, well, at 0, we definitely don't have a value of the function. We actually have a vertical asymptote. We have our points at 2/3 and f of 2/3, and then negative 2/3 and f of negative 2/3. So here we definitely have a relative maximum. It was increasing and then went to decreasing. Here we have a relative minimum. It was decreasing and then went to increasing. Around 0, it was decreasing and then continued decreasing, even though it made a kind of a massive jump right there. It actually jumped all the way from negative infinity to infinity. This is kind of maybe a counterintuitive case where the relative maximum at negative 2/3 is actually lower than the relative minimum. This point here is actually lower than this whole section over here. But the point here is not that this is an absolute maximum. It's that it's a maximum in a region around that point. It's definitely bigger than points around it. And that's all we were caring about. Well, we're not done with this section quite yet. We will move on to actually discussing the absolute maximum minimums instead of the relative ones. We can actually tackle those using calculus, but we just had to talk about relative extrema first. So we will do that in the next video. So I'll see you there.